So chapter 7 on page 483 is about rational expressions. And we're going to start with section 7.1, which is about rational expressions under simplification. So what is a rational expression? A rational expression is just a fraction where the numerator or the numerator, the denominator are either or both polynomials. So we might have a polynomial in the numerator, a polynomial in the denominator, and that is going to be a rational expression. So the rules that we learn to deal with fractions are going to be very useful for us to deal with rational expressions. See, this is just more fraction math. The only difference is that instead of having just numbers, we're going to have algebraic expressions. We're going to have, in this case, polynomials. So the first thing that we're going to learn is that there are some restrictions. So we're going to find restrictions. We're going to find restrictions for the domain of rational expressions. So I'm using the terminology that you're going to see later when you continue with your algebra preparation the next semester or after. So restrictions are just the numbers that the rational expression cannot have in its domain. So what is a domain? Domain is any value that you can use to evaluate a rational expression. So let's see if I have, for example, 3x over 2. That's a rational expression because the numerator is a polynomial. You can have 3 over 2x. That's another rational expression because you have a polynomial in the denominator. Or you can have 3x plus 1 over x minus 2, and that's another rational expression. So in the first case, you can use any number, and never then the denominator is going to be 0 because the denominator is already 2. So when you have this kind of rational expression, any real number can be used to evaluate the expression. Any real number is part of the domain. Any real number. But in the following case, there is one value that if you use for x, then this rational expression is going to be undefined. So our task in this part of the section is going to be, we need to find the number that makes the denominator equal to 0, because if you divide by 0, then you get an undefined result. So we need to find the numbers that make the denominator equal to 0, and those numbers are going to be the restrictions for the domain. So the restrictions for the domain then are just those numbers that you cannot use, because if you use them, the denominator becomes 0, and then the rational expression is undefined. So in the second case, then what is the number that makes the denominator to 0? The only way to find it is just you're going to equate the denominator to 0, and you're going to solve the equation that results from that. So in this case, you just divide by 2 both sides. So you're going to get x equals 0. This is a restriction for this rational expression. So the way that we're going to express restriction is just you're going to write x, and then you should write something that x should be different than, in this case, than 0. So these are the restrictions for this rational expression. In this other case, you have two polynomials, but again, the only one that is important at this point is the polynomial in the denominator, because it's the only one that might become zero, and if this denominator becomes zero, then we are in trouble. So we're going to find the restrictions for this case. So the restriction is, again, we're going to equate the denominator to zero. So that's what we need to do to find the restrictions. So in this case, we have x minus 2 is the denominator. We're going to equate it to 0, and then we're going to solve the equation that we obtained. So you can add 2 on both sides of this equation. So you're going to get x equals 2. So this is a restriction for the domain of this rational expression. So that means that we need to write x shouldn't be ever equal to 2, because if that happens, then our rational expression would be undefined. So this is just one important thing that you need to keep in mind, because later we're going to start simplifying, because that's the purpose of this section. We're going to simplify rational expressions. So the rational expression is going to be different in sometimes to the original algebraic expression. So we're going to lose information. So this information is very important, knowing the numbers that don't work for the rational expression, because later when you simplify the rational expression, you might be in the situation that those numbers might work, but that's not true, because you need to find the restrictions with the original rational expression. So let me solve one more problem, then you're going to solve some problems from the exercise set. So I'm going to work on example 1 from your book. Example 1 is on page 485, and it says that we're going to find all the numbers for which the rational expression is undefined. So in a short way is just find the restrictions for the domain of the rational expression. So the first case is 6x plus 12 over 7x minus 28. So this is my rational expression. It's just a fraction where the numerator is a polynomial, the denominator is a polynomial. But to find the restriction, I only focus on the denominator. So I'm going to set the denominator equal to 0 to find the restrictions for the domain of this rational expression. So in this case, it's 7x minus 28 is going to be equal to 0. And we solve the equation. In this case, you need to add 28 to both sides of the equation. So you end up with 7x equals 28. The last step, as usual, is dividing by the coefficient of the variable. So if you do that, you're going to get x equals 4. So 4 is a restriction. So usually you're going to see these rational expressions written in the following way. You're going to write 6x plus 12 over 7x minus 28, then a comma, and then you're going to see many times in books of advanced algebra that then you have something like this. So when you read this, you see that you have a rational expression, and they are warning you. You shouldn't use x equals 4, because in this case you're going to get an expression that is going to be undefined. So that's the answer for this one. So let's work on the next problem. The next problem is 2x plus 6 over x squared plus 3x minus 10. So that's my new rational expression. So then first step, we're going to set the denominator equal to 0 to find restrictions. So I'm going to get x squared plus 3x minus 10 equal to 0. And then we need to use our techniques to factor. So we're going to do a lot of factoring. So factoring is going to be a key component for everything that we're going to work in this chapter about rational expressions of factoring. So we need to factor this. So remember, we need to look for two numbers such that if you multiply those two numbers, you get a times c, which is negative 10 in this case. Then if you add these two numbers, you're going to get the middle term, which is positive 3. So what are those numbers? Maybe 5 times negative 2 is going to be negative 10, and 5 plus negative 2 is going to be positive 3. So my two numbers are 5 and negative 2. So I'm going to break the middle term. So we're going to work a lot. We're going to continue practicing our factoring by grouping, because in that way we're going to get expertise in algebraic procedures. So the leading term of this quadratic equation is x squared. Then I'm going to write the middle term as into pieces 5x minus 2x, and finally the last term. Then you factor by grouping. You have done this many times, so you know what to do. So you're gonna get x is the greatest common factor of the first group. Then you're gonna get x plus 5. Then negative 2 is the greatest common factor of the second group, and you're gonna get x plus 5 too. So, and finally you're gonna get the common factorial, the common binomial as a factor of a binomial containing the greatest common factor. So this is the denominator factors. These are the denominator factors. So then we're gonna equate every factor to 0 to find the restrictions. So if you equate every factor to 0, then you're gonna solve the corresponding linear equation. So we subtract 5 from every side of this equation. We're gonna get x equals negative 5, and also we're gonna add 2 to both sides of this other equation. So we're gonna get x equals 2. So these are my restrictions. So at the end of the day, I'm going to write my restrictions as x should be different than negative 5, comma 2. And remember, we usually write this after the rational expression. So now you're gonna practice. You're gonna solve a lot of problems from the corresponding exercise set. So you're gonna work problems from exercise set from 7.1 exercise set on page 491. So the problems that you're gonna solve are the following. So we're gonna solve. Let's see. You're gonna solve problem. You're gonna solve problem 8. X plus 5 over x plus 7 multiplying x minus 9. Then we have problem 12, which is 7x minus 14 over x squared minus 9x plus 20. And then we have problem 20. Problem 20 is just 8 over x squared plus 4. So you're gonna find the restrictions. So find the restrictions for the domain of each rational expression. So solve these problems and send me your answers, and then we're going to continue with our work. So when you're trying to find the restrictions of a rational expression like the one that is on problem 20, again, you just need to check the denominator. You're going to equate the denominator to 0. So then there are two courses of action. You either factor this, you factor the quadratic binomial, or you just solve the quadratic equation by using another algebraic procedure. I think it's the one that some of you might be tried. So when you have x squared plus 4 equal to 0, you maybe were tempted to subtract 4 from both sides. So you end up with x squared equals negative 4. And then you thought maybe if I take the square root on both sides, I'm going to find the solution. So you take the square root on both sides. So from the left hand side, you're going to get x. But from the right hand side, you cannot get the square root of a negative number. So you're not going to get a real number from this square root of a negative number. So when you are taking the square root of a negative number, you don't get a real number. You're going to get something that we call an imaginary number. We're going to see maybe that by the end of the semester, or you might cover this in the next course of algebra. So the other way to solve this is trying to factor this quadratic expression. This is the sum of two perfect squares. And if you check your formulas for special products, we only have a formula when you have the difference of two perfect squares. So you can factor something like this, but you cannot factor something like this. So you cannot factor this sum of two perfect squares, but you can factor if you have the difference of two perfect squares. So the solution for this problem is just there are no restrictions. So there are no numbers that are going to make this denominator equal to 0 ever. So try any number, you are not going to find any number making this denominator equal to 0. So there are no restrictions for this problem. So the answer is just no restrictions. So we're going to continue with our next with the next part of the same section. So we are working section 7.1, and now we're going to start simplifying rational expressions. So to simplify rational expressions, rational expressions, you're gonna factor both the numerator and the denominator, and you're gonna cancel common factors, and then this is gonna be the final answer. So let's try some examples. We're gonna start with example 2 on page 487. So we have to simplify. I'm going to simplify 5x plus 35 over 20x. So let's see. I'm going to factor the numerator first. So I'm going to write here factoring the numerator. So I have 5x plus 35. So what is the greatest common factor? you're gonna see here that the greatest common factor is 5, so you're gonna have 5 that multiplies x plus 7. I'm not going to write the intermediate steps because at this point you should be familiar with this process. If you need, you can write the intermediate steps. It is fine for me. So this is our numerator written in a factor form. Now the denominator, we can use the same greatest common factor. So let's do the thing, because what we want is to cancel common factors. So let's use this as a greatest common factor or as a factor. So if you write 20x and you're going to factor out 5, then you're going to write 5 that multiplies 20x, and you're going to divide as usual by the factor. So you're going to get 5, and 20 divided by 5 is going to be 4x. So now I have my numerator and my denominator written in a common factor, with common factor. So I'm going to rewrite my numerator is going to be 5 that multiplies x plus 7, and my denominator is 5 that multiplies 4x. So now you can cancel. You can cancel this one. So, and you can cancel this one. So they go away. So I'm going to write just arrows. I'm not going to use the diagonal because when you are checking the notes, it's very confusing to see diagonal as crossing out the number. So I'm going to use circle the number I'm going to cancel, and maybe we can just write something like an X to indicate that these are going to be go away. So what is the final answer? The final answer is just x plus 7 over 4x. So that's the answer for this one. So let's work one more problem, and then you're gonna play with the idea of getting common factors. So sometimes it's not going to be the greatest common factor, like in this case. It's just a common factor that you're looking for to cancel with the other part of the fraction, or the rational expression. So now we're gonna solve example 3. Example 3 on page 487. So now we're gonna simplify. We're gonna simplify x cubed plus x squared over x plus 1. So I'm going to do my factoring of the numerator. So I have x cubed plus x squared. So you're gonna find the greatest common factor is gonna be x squared that multiplies x plus 1. So the denominator cannot be factored, so we're gonna leave the denominator in that way. So then you just rewrite your rational expression by using the factor forms. So in this case I have x squared that multiplies x plus 1 over x plus 1. I'm going to enclose this in a parenthesis. I'm going to write 1 here. So in this case, it's not important, but when you have the numerator in this situation, it's important to write 1 because sometimes students just cancel and remove the denominator out of the blue, and that's not the right way to do it. So in this case, what is the common factor that we can cancel? It's going to be x plus 1. So I'm going to cancel this. So this goes away with this other one. So these two are canceled. So you end up with x squared over 1, which is just x squared. So that's the simplified version or the original rational expression. So you can see here that the original rational expression cannot take a number. What number? It cannot take -1. -1 is a restriction because -1 plus 1 is going to be 0 here. So it's going to make this rational expression undefined. So -1 is a restriction. But once you simplify the rational expression, you end up with a different expression, and there is no restriction for this expression at the end because it's not a rational expression anymore. So, but in this case, we should write that x shouldn't be -1. So that's the purpose of finding restrictions before simplifying. We are not doing that now because we want to learn just to simplify rational expressions, but the complete way to do the exercise is first you're going to find the restrictions, then you're going to simplify, and at the end you're going to write the answer with the corresponding restrictions. Okay, so let's see, we have one more problem. We have two more problems. Let's work first example 4 on page 488. So as you can see, it's more factoring. So it's very important to be good at factoring. And in that way, we're going to simplify our problems. Simplifying is very good because later you're going to see that simplifying is going to make rational expression math simpler. So we have x squared plus 6x plus 5 over x squared minus 25. So first, remember, we need to find restrictions. You can find the restrictions just equating this denominator to 0. So you can factor the left-hand side by using a special product. You're going to find that it's x plus 5 times x minus 5 because the difference of two perfect squares can be written in this way. So you're going to find that the restrictions are just -5 and 5. But the purpose of this problem is not this. This is just for you to get the full picture, the big picture, the full picture of the exercise. So let's start. We're going to factor. We're going to do our factoring. We're going to factor the numerator first. So to factor the numerator, we're going to write x squared plus 6x plus 5. So I need two numbers that if I multiply them, I get 5. If I add them up, I get 6. So those numbers are 5 and 1. So we can break this in two parts. So it's going to be x squared plus 5x plus 1x plus 5. Then you do factoring by grouping. So this is going to be x that multiplies x plus 5 plus 1 that multiplies x plus 5. So at the end of the day, my numerator is going to become x plus 5, the common binomial, and x plus 1, the binomial containing the greatest common factor. So that's my numerator written in a factor form. Now I'm going to factor the denominator. So I already factored the denominator here. So x squared minus 25 can be written as the product of x plus 5 and x minus 5. So you need to remember how to do these steps. If not, you need to check it back the previous chapters. So this is the factor form from the numerator and the factor form for the numerator. So we're going to rewrite this as x plus 5 times x plus 1. That's the numerator. The denominator is x plus 5 times x minus 5. Now you can see that we're going to be able to cancel a common factor. So we have x plus 5 here, x plus 5 here that we can just remove. So then we're going to end up only with x plus 1, x minus 5. That's the answer. And remember, the restrictions are -5 and +5. If you check the restrictions of this new rational expression, you're going to see that there's only one restriction. It's going to be 5. But -5 is not going to be recovered from this rational expression. That's the reason it's important to work with the original rational expression to find the restrictions. So the final answer is just x plus 1, x minus 5 with those restrictions. So that's example 4. So let me work one more problem, and then you're going to have plenty of time to work many exercises from the chapter, from this section. So we're going to work now example 5. Example 5. So let's see, example 5 is on page 490, and we're going to simplify 4x squared minus 25 over 15 minus 6x. Okay, so let's factor the numerator. Numerator goes first. So we have 4x squared minus 25. So what is the greatest common factor here? The greatest common factor, there is no greatest common factor. So then we need to see that this is a perfect square, another perfect square. So we can rewrite this as 2x squared minus, and this is going to be 5 squared. So this is going to be then a plus b times a minus b, where this is a and this is b. So the numerator is going to be just 2x plus 5 times 2x minus 5. So that's the numerator. Now let's factor the denominator. When we factor the denominator, we usually write the polynomials in descending order of powers of x. So I should write first negative 6x and then positive 15. So then I look for a greatest common factor here. So the greatest common factor is going to be negative 3. Remember, we always factor the negative sign if the leading term of our expression is negative. So it's going to be negative 3. So let's write the binomial. I'm going to divide the binomial by my greatest common factor. So I'm going to obtain negative 6x over negative 3 is going to be positive 2x. And in this case, it's going to be 15 over negative 3 is going to be just negative 5. So I have my numerator and my denominator now written by using factors. So that means that we're going to write now this rational expression as the following. The numerator is just 2x plus 5 times 2x minus 5 from here, and the denominator is just negative 3 that multiplies 2x minus 5. So now we can cancel terms. We can cancel this factor and this factor. These two are cancelled. So that means that we are removing this. Remember, I'm not using diagonals to avoid to be confusing these notes. So the final answer is just 2x plus 5 over negative 3. There is a restriction that you need to find by solving this equation. So if you do that, you're going to see that the restriction is 5 over 2. Check that later. So this is the final answer. So in your book, you're not going to see this notation. You usually see only this, but remember to be formal or strict in math, to be more precise, we need to indicate the restriction. So practice doing that, because it's going to be very helpful for you. So now you're going to solve a couple of problems from the exercise set. You're gonna simplify a lot of rational expressions. Remember, this is very important to simplify our math later on rational expressions. So later we're gonna learn about adding, subtracting, multiplying, and dividing rational expressions. So it's gonna be a lot of work, and our work is gonna be very, very simple if we know how to simplify rational expressions. So you're gonna start solving from 7.1 exercise set on page 491. You're gonna solve problem 32, 5x minus 10 over x minus 2. Then you're gonna solve problem 34. Problem 34 is x plus 4 over x squared minus 16. Then we have problem 44. Problem 44 is 3y squared plus 4y minus 4 over 6y squared minus y minus 2. So this is a problem that looks like the ones that we have in the final exam. So we have 46, 3x plus 7 over 3x plus 10. And then we're gonna solve problem 68. 68 is 9 minus 15x over 5x squared minus 3x. And finally, we're gonna solve problem 74. Problem 74 is xy minus 2x over 3y minus 6. So solve these problems, send me your solutions by using the chat box or later by sending your files through the Canvas assignment, the corresponding Canvas assignment. So now section 7.4 and the next ones are going to be about rational expression math. So we're going to do multiplication, division, addition, and subtraction. So we're going to start today with multiplication and division, and later in the next session we're going to have addition and subtraction. So what are the rules? The rules are very similar to the rules that you follow when you add, subtract, multiply, and divide fractions. So when you multiply and divide fractions, you have rules. So you multiply across when you have a multiplication, and when you have a division, you just write the reciprocal of the second fraction, and then you get just a multiplication. So we're going to do the same thing here. So the only difference that we are working with polynomials instead of just numbers. And the other thing is that you're going to have the opportunity to simplify first. So simplify first if possible. So that means that you're going to do some factoring, factor numerators and denominators if possible. So because if you simplify, then your multiplication or your division is going to be easier. So we're going to have a fraction like this. So this is a multiplication. You're going to multiply across. So you're going to get A times C and B times D. Or if you have a division, Then we're going to do some steps to convert this into a multiplication. So what are the steps? If you remember, you're going to write the first fraction the same, and then you're going to invert the second fraction. So you're going to write the denominator as numerator and the numerator as the new denominator. And then you just conduct a multiplication. So it's going to be something similar to this. So we're going to work then this section just by solving some exercises, and then you're going to have plenty of problems to work on. So let's start with the first example. Example 1 is on page 495, and this is going to be about the following. We're going to multiply 7 over x plus 3. That's the first rational expression, and then the second rational expression is x minus 2 over 5. So the best way to see numerators and denominators as units that you cannot break is enclosing those in parentheses. So if you rewrite this as 7 over x plus 3 and then x minus 2 over 5, then in that way you are not going to be tempted to cancel or to remove just parts that look similar, like for example this x and this x, you might be tempted to cancel them. But if you have these parentheses, you're going to see that this is the whole unit, so you cannot just remove one part and leave the other part and change. So then the next step is simplifying. So can we factor any numerator, any denominator in some way? No, there is no greatest common factor for this binomial. There is no greatest common factor. So the only thing that you can do is just multiply across. So you're going to have 7 times this. This is going to be 7 times this over this binomial multiplied by 5 is going to be 5 times x plus 3, and then you just apply the distributive property. So you're going to get 7x minus 14 over 5x plus 15. So I'm applying the distributive property in both cases, and that is the final answer. Sometimes you can leave the answer in this way. It depends on the book, but the most important thing is that you are doing the multiplication and that you are doing the simplification if that is possible. So now we're going to work another example. So we have example 2, that is on page 495 2. So we're going to multiply x minus 3 over x plus 5, and we're going to multiply this by 10x plus 50 over 7x minus 21. And again, to prevent mistakes, use parentheses to enclose any numerator, any denominator. This is not the way that is written in the book, but for us is a good thing to do, because in that way we prevent just removing pieces because they look the same. So now, can we factor any numerator? Can we factor any denominator? Yeah, you can see here that we can factor this. There is a greatest common factor for this one. There is a greatest common factor for this one too. So instead of multiplying across and getting huge quantities here, a lot of terms, first let's see whether simplifying is going to get our life easier. So let's do this factoring. So I'm going to do factoring. I'm going to do factoring numerator 2. This is the first numerator. This is the second numerator, first denominator, second denominator. So I'm going to do factoring from the second numerator. So I'm going to factor 10x plus 50. So what is the greatest common factor here? The greatest common factor is 10. And you're going to get x plus 5. Then I'm going to do factoring of the second denominator too. So I'm going to do factoring of denominator 2, which is this one. So it's 7x minus 21. So what is the greatest common factor? The greatest common factor is just 7. And 7 multiplies x minus 3. So now we're going to rewrite everything by using the new versions of our numerators and denominators. So we're going to get x minus 3 is the first numerator. And the second denominator is 10. So I'm going to use a parenthesis before 10. And also x plus 5. Then we have the second, the first denominator is going to be x plus 5, and the second denominator is just 7 multiplies x minus 3. I'm just writing just a single fraction bar now, indicating that I'm doing the multiplication of numerators and the multiplication of the denominators. Just by writing a single fraction bar means that I proceeded with the multiplication. So this is the result of multiplying these quantities. I haven't finished my work because first before applying distributive property or something else, I need to see whether I can cancel common terms, common factors. So, and by canceling something, I mean the entire parenthesis, not pieces or parts of every parenthesis. So, are there any factors that I cancel? Yeah, I have this x minus 3 complete the entire parenthesis and this x minus 3. So this goes away and this also goes away. Is there any other common factor? Yeah, we have x plus 5 on the top, x on the bottom. So I need one from the top, one from the bottom. I cannot cancel both or two common factors if they are on the same side of the fraction. You need to have one from one side and the other from the other side of the fraction bar. So we remove everything, so we end up only with 10 over 7. So that's the beauty about simplifying first, because if you don't know about simplification, you just start multiplying everything. You're gonna get a huge trinomial here, and then another huge trinomial. Then you need to factor those trinomials, and you're gonna go back to these expressions that are here. So that's the reason it's better to simplify first before doing the actual operation. So let's work more problems. Let's see, I have 4 more problems. So we have a lot of work to do. So let's work now one more case. So we have now example 3. Example 3 is on page 496. So we're gonna multiply two rational expressions. The first one is x minus 7 over x minus 1, and that's the first one. The second one is x squared minus 1, 3x minus 21. So first thing, enclose in parentheses every numerator and every denominator. So I'm going to write this as an extra step. X minus 7, x squared minus 1. I can use a single fraction bar now. So I'm just indicating the multiplication that I haven't finish the operation. So now let's factor things. So I'm going to factor x squared minus 1. So you can see that this is a perfect square, is x squared, and this is also a perfect square. So this is a b, that's the difference of two perfect squares. So you know that you're going to use a plus b times a minus b. So this expression is going to become a is x plus 1 that multiplies x minus 1. So that's the first factoring. Then I have this one here. So I'm going to factor now 3x minus 21. So to factor this, you only see that you can get the greatest common factor out of this, which is 3, and then you just end up with x minus 7. So that's the other expression that you can factor. So now I'm going to write everything by using the new versions of every expression. So I have x minus 7, this one here. Then this x squared minus 1 becomes x plus 1 times x minus 1. So we need to be very careful that we don't lose anything. So then I have x minus 1 here, x minus 1 here, and then 3x minus 21 is going to become 3 times x minus 7. So now we check for common factors between the numerator and the denominator. So let's see, I can see here that x minus 7 appears here and x minus 7 appears here. So the entire thing, the entire parenthesis. So you remove this, you remove this. Also, we have x minus 1 here and x minus 1 here. So they go away. So we end up only with x plus 1. You need to write your fraction bar always, because if you end up with nothing on the top, then you write 1. So there are times that you're going to remove everything that you see in the numerator and you say, oh, then you just write the denominator. That's not the answer. The fraction bar should be there. And then if you get nothing in the numerator, you write the number 1. In this case, we are ending with x plus 1, and the denominator only contains the number 3. So that's the final answer. Okay. So let's work on the next example. We have example 4 on the same page. Example 4 is it's a huge multiplication, but thanks to factoring, it's going to be simplified before doing any extra operation. So we have 4x plus 8 over 6x minus 3x squared, and that multiplies 3x squared minus 4x minus 4 over 9x squared minus 4. So that's what we have. So what is the first step? Enclose the numerator, the denominator, everyone in parentheses. So that way you see every component of your rational expressions. So now we're going to start factoring things. So let's see, we're going to start factoring this numerator. So I'm going to factor 4x plus 8. So what is the solution for this problem? You just get the greatest common factor, which is going to be 4, that multiplies x plus 2. That's my first factor. Then We can go in different order. Doesn't matter as long as you put everything into the right place at the end. It doesn't matter. So I'm going to continue with this one now. I'm going to factor 6x minus 3x squared. So what is the greatest common factor here? The greatest common factor is going to be 3. Negative 3, because this is the leading term. This should be first. So you can write this as negative 3x squared plus 6x. Remember, in descending order of powers of x. So now, what is the greatest common factor here? Is negative 3x. So, and then you can divide every piece. If you are not sure on how to proceed, do it in the old way. It's gonna take longer, but it doesn't matter as long as you get the right answer. It's worth it. So you're gonna get negative 3x that multiplies x only, because this negative 3 and this the negative 3 cancel, and then we have negative 6 over 3 is going to be 2. So that's the factor for this term. Now I'm going to factor 3x squared minus 4x minus 4. So now I'm looking for two numbers that when I multiply those numbers, I'm going to get the product of a and b, so it's going to be negative 12. And if I add them up, I'm going to get negative 4. So what about 6 and 2? Negative 6 and positive 2. You're going to get negative 12, and you're going to get also, if you add them, you're going to get negative 4. So this trinomial can be written as 3x squared minus 6x plus 2x minus 4. Then you factor by grouping. So you're going to get here 3x, and then the factors are x minus 2. Here you factor 2, and you get x minus 2. So the final answer for this is going to be x minus 2 that multiplies 3x plus 2. So that's the next expression being factored. So now the last one, I'm going to factor 9x squared minus 4. So this time we have again the difference of two perfect squares. So you can see here that you can write this as 3x squared minus 2 squared. So you get your a, you get your b. So you know this is going to be 3x a plus b, 2, that multiplies the conjugate, which is just 3x minus 2. So I have everything now, factor. So we're going to rewrite this thing over here. So 4x plus a first is written as 4 times x plus 2. Then I have 3x squared, and I have a huge fraction bar here for everything. I have 3x squared minus 4x minus 4. You go here and you find x minus 2 that multiplies 3x plus 2. Then denominators, 6x minus 3x squared is over here. The final answer was negative 3x that multiplies x minus 2. Finally, the last denominator, 9x squared minus 4, is going to be written as 3x plus 2 times its conjugate. So now I have everything here. So now I can cancel things. I can, in your book, you're going to see just diagonals. Let's use our new system to eliminate things. So I'm going to eliminate this one, with this one. This goes away, this goes away too. What else? I have this x minus 2 here, this x minus 2 here, so this is also being removed. And it seems that this is there are no more things that are common. So you're gonna write the final answer. So the final answer is just writing what is left. So let's see what is left. From the numerator, we are left with 4 that multiplies x plus 2. From the denominator, we end up with negative 3x and times 3x minus 2. And that's the final answer. Okay, so we finish this problem that way. So we don't need to do the distributive property and things like that. So that's the way that we end up showing the answer. So I'm going to work, we have divisions. Okay, we're gonna stop here for a moment for you to solve some exercises, and then we're gonna do division. So let's see. You're gonna work some multiplications now. So let me find some for you. Okay. You're gonna go and check 7.2 exercise set on page 498. So you're gonna do a couple of multiplications, not many. So I want to give you problem 10. So you're gonna multiply. Problem 10 is just x squared plus 9x plus 18 over x plus 6, and this rational is expression is multiplying 1 over x plus 3. And the other one that you're gonna work is problem 12. Problem 12 is just gonna be x squared minus 49 over x squared minus 4x minus 21, and this rational expression is multiplying x plus 3 over x. So work these two only, and then we're going to continue with a couple of examples where we're going to divide rational expressions. Okay, to work division of rational expressions, what you're going to do is just an extra step with respect to multiplication, which is just you're going to express the division as a multiplication by inverting the second rational expression. So let's work a couple of examples. So we have example 5 on page 497. So now we're gonna divide x plus 5 by x minus 2 over x plus 9. So what is the first thing? When you have an expression like this that is not written in a fraction form, you need to write it in that way by getting a denominator equal to 1. So you need to write everything as fractions. So this is the first one. Then you have the operator for division. And then remember, you're going to enclose in parentheses every numerator and every denominator to prevent mistakes. So once you have that, the next step is just inverting the second rational expression. So we're going to take the reciprocal. That's another way to say the same thing. So invert the second fraction or rational expression, which is just take the reciprocal. That's the other way to say this in a more mathematical way. Take the reciprocal. So how do you do that? You're going to write the first fraction in the same way, the same form. Then you're going to remove this operator for division. You're going to write the operator for multiplication. And then you're going to invert the second one. So by inverting, you're going to write the denominator is going to become the numerator, and the numerator is going to become the denominator. And don't forget enclosing in parentheses every piece of these fractions. So now we're going to multiply across. Of course, you need to check whether there is something that you can cancel, you can simplify, but in this case, there are no ways to factor this further. So you just multiply across, and that is going to be the answer. So the answer is just getting a single fraction bar, then you write your numerators and you write your denominator. So this is the answer. So that's example 5. I'm going to work 2 more examples, and then you're going to have an opportunity to play with this new method. Okay, so we're gonna work now example 6, which is on page 497. So we're gonna divide, and we have our first rational expression is x squared minus 2x minus 8 over x squared minus 9, and this is divided by a second rational expression, which is x minus 4 over x plus 3. So this is the way that the exercise is presented in your book. You're gonna use your parentheses. What is the reason of doing that? Remember, these are units that are unbreakable, so you cannot take just part of this and cancel with part of this. No, we just cancel factors, and factors is something that is enclosed in a parenthesis. So let's convert this into a multiplication. So to do that is you're going to write the first fraction in the same way. So that's my first fraction. Then we're going to use the multiplication operator, and then you're going to invert the second fraction. So you're going to write the numerator as the denominator as numerator, and the numerator as the denominator. So now it's a multiplication. Now we're going to factor everything that is factorable. So let's start with the first numerator. So I'm going to factor x squared minus 2x minus 8. So to factor this, you're going to look for two numbers that when you multiply them, you get negative 8. And if you add them up, you get negative 2. So those numbers might be negative 4 and positive 2. So the product is negative 8, and the sum is going to be negative 2. So that means that you can write this as x squared minus 4x plus 2x minus 8. Then you do your factoring by grouping. So you're going to get x that multiplies x minus 4 plus 2 that multiplies x minus 4. So the final answer is just x minus 4 multiplying x plus 2. So that's the factor for the first one. You cannot factor this, you cannot factor this, so the only one that we can factor is this other piece, this denominator. So we're going to factor x squared minus 9. So you can see that this is a perfect square, this is another perfect square, and this is a difference. If this was a sum, then you cannot factor anything, but this is a difference, so that means that we can write this as perfect square. So this is my a, this is my b, so you're going to write x plus 3 times x minus 3. So that's what we have. So now we're going to rewrite everything by using a single fraction bar. So in other words, we are multiplying now, although we're going to leave the multiplication indicated only. So first numerator is x minus 4 times x plus 2. Then we have x plus 3. Then this denominator is over here, so it's going to be x plus 3 times x minus 3. And finally we have x minus 4. So check everything. Don't leave anything unchecked, because you can make mistakes. We can miss parts. Then we're going to cancel common factors, one from the top, one from the bottom. So for example, this one, this goes away, and this is going away too. We remove these two. Then I have x minus 4, x minus 4, these two disappear too. So we end up only with x plus 2 over x minus 3. So one more exercise, and then we're gonna have problems for you to work on. So we have example 7. Example 7 on page 498. So we're gonna divide again. So this time my first rational expression is, the numerator is y squared plus 7y plus 12 over y squared plus 9. And the second rational expression is just 7y squared plus 21y. So that's what is given by the book. So we're going to include also parentheses for the numerator and denominator corresponding to the first rational expression. So we're going to start adding also a denominator here. So we need two rational expressions, we need two fractions. So now we're going to convert this into a multiplication. So we're going to write the first fraction is going to stay the same. Then we're going to write the operator for multiplication, and then we're going to invert the second one. So we're going to write 1 on the top and 7y squared plus 21y. So that's our multiplication, our division converted into a multiplication. So now we're going to factor some pieces of this rational expression. So we're going to factor y squared plus 7y plus 12. We're going to factor this first. So I need two numbers that when I multiply them, I get 12. If I add them up, I get 7. So 4 and 3, right? 4 times 3 is 12, and 4 plus 3 is 7. So you're gonna rewrite this as y squared plus 4y plus 3y plus 12. Then you're gonna get your greatest common factor from the first group. So it's gonna be just y that multiplies y plus 4. Then the greatest common factor for the second group is just 3 that multiplies y plus 4. So this is gonna be just y plus 4 that multiplies y plus 3. So that's one. The other one that can be factor is this denominator. So we're going to factor 7y plus 21y. So you're going to get the greatest common factor is just 7y that multiplies y plus 3. Okay? And finally, if you are thinking of factoring this, if you think, oh, I can factor this because these are perfect squares, you have a sum here. So it's the sum of two perfect squares, so no factors. No factors. There are no ways to factor this. So it's a prime binomial. So let's just write everything now. So I'm going to write this rational expression here by using a fraction bar, a big fraction bar. Then I have y squared plus 7y plus 12, which is over here, and is going to be written by using this factor form. So it's y plus 4 times y plus 3. Then I have just number 1 there. Then the denominator, we said that we cannot factor y squared plus 9, so it's going to stay there. And finally, this denominator was written or can be written as 7y that multiplies y plus 3. So that's what I have. Now I'm just going to look for common factors that can be cancelled. So you have y plus 3 here. That goes away as long as you remove this one too. And it seems that that's all what you can do. So you're gonna get just y plus 4 in the numerator. You're gonna get 7y that multiplies y squared plus 9. So that is gonna be the answer. Okay, so now you're gonna work on some exercises to finish our lesson today, and you're gonna have a time after if you want to review the lesson. So you go and check 7.2 exercise set on page 499, and now you're gonna work on problem 44. So you're gonna divide x squared minus 4 over x minus 2. You're gonna divide this rational expression by x plus 2 over 4x minus 8. Then you're gonna solve problem 54, and that is gonna be all for today. 54. 54, the first rational expression is 3y squared minus 12 over y squared plus 4y plus 4. You're gonna divide this by y cubed minus 2y squared over y squared plus 2y. So you're gonna work on these two exercises and you're gonna send me your answers either by using the chat box or by uploading your results, your PDF file through Canvas and by using or pressing the submit button. And that is all for this lesson.